Okay, hello everyone. Welcome to day 2 of the DeSIRe online course. Thanks, as always, thanks for joining us, and I hope that you will participate with interesting questions and comments. So thanks again. And then let me start with today's course. What we're going to do is to continue covering the basics of the code. Today, I will go through all the files that we need for running both synthesis and inversions. I will go step by step, covering them one by one. And in general, in broad terms, I will try to explain you what each file does and what each file contains. But then we will have much more in-depth studies in the next class. In the next class, we will have a lot of examples where we change things and we evaluate how they impact on the synthesis or the inversions. Well, next week and next class will be synthesis. So then the idea is that we, as we said in the beginning, we are combining DeSIRe and RH. So then you will see that we are also combining some of the files for each code. So you can see that we will have a top part that it will be the DeSIRe control file. And you will see that it's very similar to the DeSIRe one. And then this file will control DeSIRe files, will command and will read the information contained in the DeSIRe file. And those files will be the atmosphere, will be in DeSIRe format. Stokes profiles will also be in the DeSIRe format. The information of the lines, if you remember that we covered that a long time ago, but we had a file where we specified the atom, the information, the wavelength, the ionization values, everything. So this file is the same here with just minor differences that we will cover later. Also, we provide the information of the spectral range we are going to cover with the code and the spectral sampling in the grid file that is the same again with DeSIRe. Then we provide the abundance file in the same format as DeSIRe. And we also have a new file that is called a solar coordinates. I think it was also available in DeSIRe. And here we just provide the position on disk of our observation, and then the code can read it. I add here a plus, and later on I will emphasize this. But the idea is that some things like the abundance, we are keeping everything consistent. So we only provide one file, in this case is in the DeSIRe format, but the information contained there is the same that we will use when we are running the RH model. So for example, abundance is an important thing. We are forcing the code to have the same values for all the modules. So then everything is consistent. Okay, so then, but the DeSIRe control file also will control some files that are related to RH. First one will be the keyword.input. And then this keyword.input, as you saw in the previous tutorials, they will define the atoms that we compute. It will go to look for those atoms and check information inside the atoms and also molecules. So then the structure is something like this. I include these arrows to just tell you that sometimes they are connected. So sometimes you define something in one file, and then it is, for example, in the RH case, you define something in the atom, inside the atom file, and then this is translated to something in the wavelength file on the lines file. So then there's a smooth interaction and communication between them. Okay, so then today I will go one by one, showing you a reference case and explaining you the general things that you need to include there, although we already cover most of them in the DeSIRe and RH courses and tutorials. But the important thing is that I will probably move a bit back and forward between these two sides of the diagram. And this is because DeSIRe is built like this. So it's combining DeSIRe and RH, so then it means a really close interaction between both modules. Although for the code is essentially one big package, and for you, it will be like that. Although if you are already using DeSIRe and RH, you will see a lot of similarities. Okay, then miscellaneous section. I think I have 3 entries here. So the first one is that Alberto sent me a question about something that he found in the example run. He was asking me why the observe profile was called observe.spc instead of .pair. That is the one that we use. And in fact, in the previous diagram, I was saying that the Stokes profile is a .pair. And the idea is that this is a new option that we added. And we usually, for inversions, because usually observations are normalized to a continuum, local continuum in general. So then traditionally, when you feed inversion, when you do inversion, when you feed observations, when you do inversions of those observations, they are normalized to a local continuum. So then we always normalize the profile. But as now we are using RH and we are getting information from RH, we thought that it would be nice if you want to have the profile in physical units, that is the ones that RH provide, then it would be also a possibility. So if you specified that the profile has an extension SPC, it means that the final profile that you are going to get is not normalized to the local continuum intensity. It's just that. And in fact, he also asked me, and I forgot to explain it probably in the last class. So in the example folder, you have to first run the synthesis.dtroll. So then you generate this profile, and then you run the inversion. So then it's a double check. So you first run the synthesis and you check that everything works, and then you run the inversion and also you check that everything works. Because the observe.spc is not in the folder. So we thought that it would be better if you run the synthesis, everything works, and then you move to inversion. Okay. So then again, I will try to go to this in future tutorials, but I just wanted to tell you that the example is correct. It's just that we are adding a new option, and I thought it was explained here. I hope you follow the explanation. Okay. So then I think this is one important one. So I will try to continue the class, even if you said yes, but have you tried to run the code? Have you experienced any issues trying to compiling the code, or did it work for those that tried?
It didn't work for me on my Mac.
Okay.
But it worked on my HPC.
Okay.
So, which is where I intend to run everything anyway. So I'm not really worried about it. I think it was a G4 problem on my Mac.
So your Mac is a new one with Apple Silicon, or is a previous Intel X?
It's an M1.
Okay.
So
okay.
And it's Monterey is the operating system it's
running
for the minute.
Yeah. Yeah, I think it's architecture. I tried last year with an M1 and I didn't succeed. So I want to try with a new one that is also an M1. But I think it's probably that, and I want to look at that. So I will talk to Basilio, Han, and Esperanza, because the architecture is different. So maybe there's some just miscommunication between the compiler and the makefile. So I will test it with my computer, because it's also M1, and also Basilio, you have an M1. So we will try it there, and we will check what is happening. But in principle, Ryan, you said that in the big machine, traditional x86 was working
well. It was
well.
fine. Yeah, it was fine.
Okay. Okay. Good. Okay. So I take note that of Apple Silicon issues, and then next week, next class, I hope we will have everything fixed. Okay. So does anyone have any other issue, or was okay? Okay, I assume that was fine. If not, just send us a mail, and then I will try to check it with Basilio and Esperanza. Okay, also, I think the other Ryan asked in the previous class if Python routines were available for running just simple things like writing an atmosphere, reading the atmosphere, writing profiles, reading profiles. I talked to Ricardo, and he's here today, and he made the modules for doing those tasks inside the parallel wrap. So then they are available, but they are not as a standalone Python routine. So then he's going to do that. It will take a bit, maybe a few weeks, but hopefully in March, we will have standalone Python routines that are the same. So writing an atmosphere, reading an atmosphere, writing profile, reading profile, reading response functions and everything that I'm usually doing in IDL. We will try to provide those Python routines, hopefully in a few weeks. Okay. Okay. So then let's start with interesting or more, yeah, I think it's more interesting part. So as always, I will be inside DeSIRe, then run, and then in this case, it will be day 2. So this is a procedure that is inside that folder, and it's really a lot of text. I think this can be seen as a manual, so maybe I hope that is going to be very useful. And then we will just run it as an IDL script, because at the end we will just run a quick sample. But basically, this is just a script with a lot of information related to all the files. Okay, so today my plan is to just go through the text and then show you the files that I describe in the text in this column. Okay, so in this separate script. Okay, so then day 2. As I said, we have a mix of SER and RH files. So then let's start with the first one. This is the control file. So for example, in this case, it's called synthesis because we are doing the synthesis, but you can call it any name that you prefer. And for those familiar with SER, you will see that it's essentially the same in the first part. So I will quickly just check it with you. So remember that this is cycles. So -1 is computing response functions, 0 is synthesis, and values larger than 0, it will be inversions. And the number of cycles will be defined by the value. We are calling the profile file, as I said. We are also have the possibility of adding straight line, PSF. So this will be covered later. The important thing is that we always need a grid file. We also need the information regarding the lines, the abundance, and in the case, in this case, synthesis, well, in both cases, you also need an atmosphere. Okay. As I said, you can also specify the coordinates where you are going to where your observation was performed. And then you have this is essentially inversion part. So we are not going to really cover it today. And the idea is that we covered this in detail for the SER course, so we will revise it in the future. But essentially today I want to focus on these new lines that are added and they are exclusive from this side. Okay, so then the first one is called non-LTE threshold. I will try to explain it, and maybe it will be a bit difficult for you to follow it now, but when we do inversions, I will repeat it again. But the idea is we wanted to have the possibility of allowing the code to just do LTE, and then it will mean just basically SER, that is really, really fast. And you can tell the code that if you put 10, for example, or a larger value, but we also wanted to have the possibility of forcing the code to evaluate the departure coefficients in every cycle of the inversion. So then this will be a 0. So then every time that we run a cycle, we transform the atmosphere, we compare how the synthetic profiles, how similar it is to the observed one. And then we run a new cycle, but before that we compute the departure coefficient. So every cycle we are running the non-LTE solution. This is probably the most accurate way, but it's also the slowest one. So we also wanted to have the possibility of saying, let's define a threshold where you can assume that your departure coefficients are still good enough if the atmosphere has not changed too much. And then you can speed up the process between cycles. So then if you have different numbers, then you can set, if my temperature didn't change too much between one cycle and the other, then the departure coefficients are still valid. So then you don't need to run the nonempty problem again. So then you can speed up the inversion. And this is given different values. Basilio, I want to confirm. So if I give 1 here, this means a change of 10%, right, in the temperature?
I don't really sure. I think it's 100%. I think this 0.1 is a 10%.
Okay, so then
I need to check.
Okay, so I will put here 0.1 and then
yes, I think it's a 10%.
Okay.
Yes.
Okay, so then 0.1 would mean that if the temperature in any place in the atmosphere change between one cycle to the other more than 10%, then you reevaluate the departure coefficients running the nonempty problem. If the changes are smaller than that, then the code goes through with the same departure coefficient, but then changing the atmosphere.
Exactly.
Okay. Okay, thank you. So then, and as always, if you see that something is not clear, just stop me. Okay. I know that this part is going to be a bit difficult, but I promise that we will revise it again in future classes. Okay, number of rays. So if you remember, this was an input parameter from RH. So you can tell the code how many rays in the heliocentric angle you want to compute to solve the nonempty problem. And we thought that this is a very important parameter because it really changed the results. So we wanted to have it here in the keyword, in the control file of DeSIRe. So then it means that now we are telling RH, when we call RH, in the keyword.input, how many rays we want to have. So usually, if you remember, 5 was like 1, 0.75, 0.5, 0.25, and almost 0. And 3 is going to be something in the middle, like almost 1, 0.5, and then almost 0. So I think it's a reasonable approach. But between 3 and 5 is probably a good configuration. More than that, probably will not change too much, but it will slow a lot the code. And below 3, probably the nonempty solution is not so accurate. So at least between 3 and 5.
Yeah, the main idea of introducing this in the control file is that in every cycle you can change that. You can put here 3 inputs, 3, 5, 10. Yes. If you put that only in the keyboard is the same for all the cycles.
Yes.
Then it was mandatory to put here in order to be able to, for instance, doing a first cycle, doing a first cycle with less accuracy and then increase that for later.
Yes. Okay. Yeah. So you can see that you can do it like nodes in the temperature or nodes in the magnetic field. Okay, Dato, I think you have a question.
Yes. So Carlos, if you are running inversion, then do you need to specify anything for number of rays?
Yes. So these files are mandatory on both synthesis and inversion, because so unless you are doing LT inversions, but if you are doing normal inversions, if you are computing the departure coefficients after solving the nonempty problem, then you need to have the information about rays, because we need to solve the spectrum, and has to be compatible with the atomic population that we are computing in nonempty.
If you are not, sorry.
Yeah, go ahead.
Yes, if you are inverting the specific observations with specific mu angle,
yes.
I guess you should select that number of rays in a way that one of these should be the observed mu, right? Or
no, so I can try and then Han will do it perfectly. So the idea is that when you're solving the nonempty problem, you have to cover different heliocentric angles just to have the consistent solution. So it doesn't matter where you are on the disk, it's just to have the full consistent approximation between spectrum and populations, and have everything consistent. And now Han will say it in a proper way.
No, they are basically unrelated, the two. As Carlos said, we need the angles in this that are specified here are needed to properly estimate the relative rates. So to estimate the relative rates in a non-LTE problem, you have to integrate over all the solid angles, right? And that's what this angular grid does. And also, you cannot just to make that as accurate as possible. These are Gauss-Legendre polynomial zeros. So you typically won't hit exactly the observed angle. And so what the code does is then, after getting the proper non-LTE solution by having the evaluated all the relative rates properly, you can, given the population numbers from that solution, you can calculate the solution at a particular angle, which is the one that you specified for your observations.
I understand it now.
Yes, yes.
Thank you.
Yes.
Okay.
Yes. Yeah. Just as a quick comment, that if you remember, or everyone, if you remember, this was what we did with RH. So when we solved the non-empty problem with RH, we gave a certain number of rays. Usually it was 3 and 5. But then after that, we called the solve ray procedure, and there we were specifying one single heliocentric angle, and this is the one that you finally get. But the idea is that before that, the better you cover the different heliocentric angles, that last call for solve ray is probably going to be more accurate. Okay, so then 3 and 5, it's going to be a good solution, and you have always to provide it there. Okay, so I will continue. Then integration method. So then the idea is that you can define in this control file what type of integration method you use for the source function. So in the past, the default integration for SER was a polynomial Hermite integration method, and then RH had quadratic, I think it was an interpolation method, but then we added the DeSIRe cubic, and now we wanted to have everything consistent. So the idea is that now we are always integrating, if you want, the source function in RH and in SER modules inside DeSIRe with the same integration scheme. So everything is a bit more consistent. So the idea is that by default, you set 2 here. That it means DeSIRe cubic, and RH also by default will do this. We will use the same integration scheme. So we are trying again to have everything as consistent as possible. Okay, so then final evaluation of the profile. This means that, so let me see if I forgot. Yeah, I think it's related with non-empty threshold, but essentially what we are going to do always is that when you finish the inversion cycle, it doesn't matter if in that cycle or the previous cycle we computed the departure coefficients and we call RH, we are going to always call RH with the atmosphere that we have from this side, with everything that we have from this side. So then the final profile will be the best we can have. But imagine that you are running a 5-cycle inversion and you want to have the best profile in every cycle. So then you can force the code to always solve the non-empty problem, to solve the right transfer equation and compute the profile with RH in every cycle. So then you can say, okay, I want to test the difference between 2 cycles and 3. So then you put there a 0, I think. Yes, I think it was a 0, a 0 or a 1.
No, the opposite. If you put
1.
0, you are not evaluating.
Okay.
If you put 1, you are evaluating.
Okay.
In every cycle.
Okay, 1, I will put not here. I will just add it later. Note 1 always.
Yeah, exactly.
And I will polish this later.
Yeah.
So then if you said, I know that I've always run 4 cycles and I just take the last one, so then 0. And then if you want to compare between the second cycle and the third cycle, then just put there 1, and then you will get all the information, all the output information from each cycle. So then you can compare. For example, imagine that you said, I want to check the difference between 3 nodes in temperature and 5, because maybe 3 could be better. So then you put there 1, and then you compare the profiles and the results from both cycles.
Yeah, in the set option, you save some time, but
yes.
okay.
Yes. Yes.
You don't have all the information. Okay.
Yes. Okay. So then, and the final one is so we are going to provide the atmosphere in SER format, and this will be read by the side, and then this information will be passed to RH. So if you remember, RH had a different convention for atmosphere. It was using thermal part and then hydrogen populations, and we had the option to provide in the height scale geometrical height, mass column, or optical depth. So then we wanted to have things again as consistent as possible. So you are going to work with models in optical depth. This is the ones you are going to provide to DeSIRe. So we wanted to have the option of passing the same atmosphere to RH directly. So then internally we are going to compute the hydrogen populations in LTE, but this is very quick to do. And then the same atmosphere that we are using for the SER part, let's say this way, it's going to be also transferred to RH. But if you prefer to use a different height scale, in this case, mass column, you just need to change here. And then what we are going to do is that from the atmosphere that is in optical depth that we are providing as an input, we compute the mass column, we transform the atmosphere, and we pass it through RH. Okay, so both options are possible. Okay, any question until now? I will repeat this a lot of in the next classes. So if you feel that it's a bit difficult, don't worry. But just in case that you have now a question, I can try to answer it. No? Okay, so then let's go to something that is a bit more, that we are more used to. So it's the atmosphere, okay? Remember, it was 3 values at the beginning. It was microturbulence, filling factor, straight line. I just put here some explanation, but this was in kilometers per second. This goes from 0 to 1, where 1 is 100% filling factor, and this one goes from 0 to 100, where 100 is 100% of a straight line. Okay, that hopefully will not happen. Okay, then we have 11 columns, optical depth, everything in CGS. So temperature, electron pressure, microturbulence, field strength, line of sight velocity, magnetic field inclination, magnetic field azimuth, geometrical height, in this case in kilometers, and then again in CGS, the gas pressure and the gas density. Okay, is exactly the same we had for SER. And now the only thing is that we are going a bit higher in the atmosphere because we are going to synthesize and invert chromospheric lines. So you can go up to -8 or maybe -7. It depends on the lines that you are going to study, but you have to go high. You cannot stay up to lockdown -5 or something like that, like we have in SER. Okay, then profiles. Again, this will be easy for those of you that follow the SER tutorial. So the first one is the index, where the code, so you tell the code which line you are providing through this index. And we will look at later, it will be in this line file. Then it will be wavelength in milliangstrom and respect to the line core, to the rest line core that you are providing in the lines file. Intensity, Stokes Q, U, and V, all of them normalized to the local continuum, computed with the HSRA atmosphere. Okay, so we had compute all the continuum with the HSRA atmosphere from all the wavelengths that you can cover, and then we are normalizing always to the local continuum close to the continuum of the line that you are synthesizing. Okay. Okay, I think yes, and what I said before, so this is the normal one, but you can also specify this SPC, and then it would mean that instead of being normalized to the continuum intensity, it will be just in physical units. One thing though, always we will have the Stokes profiles in a uniform spectral sampling. Okay, so this is something that we had from SER, and we will also have it here. So in the grid file, you will always provide only the beginning and at the end of the spectral range, and then the sampling. And then the code will compute a uniform spectral range with these three values. Okay, so then the lines file. So as I said, this index is pointing to a transition that is described in the lines file. So then here, for example, it was saying 4. So then it's pointing to this transition. Okay, that is the calcium 8542 line. And very quickly, just this index, the element, the ionization stage, wavelength in Armstrong. Then this is the enhancement factor. I said here that is obsolete in general. We can discuss this in detail later. Sometimes if you are using a new line that has not been observed before, maybe you want to tune this value a bit. But in general, for the well-known lines that we are covering here, you can leave it as a 1. And also we are discussing, although it's not confirmed yet, that we may change this to a different option. But the idea is that the main reason is that when you have new lines, you don't know exactly the atomic information, you just try to do an inversion and try to fit, and maybe playing with this value, you can get a good fit. And then it means that something is missing in the atomic information. It could be the Loggf or other parameters, and you are correcting that with this enhancement factor.
Yeah. In general, if you don't have the Barclay coefficient that you will speak later, the program is using the Unsol formula. The Unsol formula, in general, introduces a very low width of the line, and then you need to enhance this with this. This is a very old, because in old times, when people usually regularly use Unsol formula, discovered that the lines were very narrow, and then introduce this enhancement factor in order to increase the width of the line. But if we have the Barclay coefficient, we don't need that. Yeah. But in some cases, you don't have. Of course.
Okay, thank you. So then the next one is the Loggf that I think I forgot here, so I will add it. Sorry. So here it should be, there should be a 6. That should be Loggf. I will explain it later. This is, you can find it in the database, or someone else has maybe computed it empirically. Then the ionization energy, that is usually, you just look for the lower level with lower energy of the transition, and then transform it to electron volt, and then you put it here, just that value.
It's the opposite. The first is this. The second is the Loggf.
Sorry.
The first,
yes.
Yeah.
Yes.
Okay.
So sorry. So then it should be. I move it down. Sorry. Yeah. Okay. So then. Thanks, Basilio. So then this is the Loggf. And this, as I said, it's in electron volts. So usually you can change it, but sometimes you work in centimeters to -1. So then just be sure that it's in electron volts. Then Loggf, and then we start with the spectroscopic information of the lower level. Always we go lower and higher level, upper level. And then it's this first one is the spin, so 2 times spin plus 1. Then this is the information here related to the linear angular momentum. Remember that the S, P, D, F, G, and S is always 0. And then the total angular momentum, and then you have the same notation for the upper level. And this is what Basilio was talking about. So these are the 2 enhancement parameters due to collisions with neutral hydrogen. And remember that we had 2. I think the first one is alpha. Yes, alpha. And then the second one is a sigma. And remember that from the program, the cross-section program, we got it in different units, and we had it to put it in CGS units for SER. So sometimes, or for DeSIRe. So sometimes in the papers, it will be a much different value. So then remember that you need to transform it to CGS. Okay, so this is the same for all the lines. And it's also the same for SER. But there are two new columns that are related to non-LT transitions. And this is what I added here, sorry. I will change the numbers, so it will be 11 and 12. Sorry, I'm still recovering. The idea is there are two values and they correspond to the index of the atom level involved in the transition. Okay, I will go fast to that and then we will check it later again. So if you are using an atom, remember that in RH an atom looked like this. So you had a list of energy levels, okay, and they have assigned an index, okay, 0, 1, 2, 3, 4, 5. And then you had defined the transition, for example, in this case, 8542. And then you see that it says that it's between index 4 and 2. Okay, so then what we are saying here is that the transition is between level 2 and level 4. Again, it's always lower and upper level index. So we are telling the code exactly which levels are involved in the transition that we are using, which levels of the RH atom are involved in the transition. And this is because we want to compute the population and non-LT of those levels to compute the departure coefficients. So then, as I said, there's going to be a close relation or communication between RH and SER. And this is one of the cases. So you have to specify where these transitions or which levels are in the atom file correspond to this transition. And this is very important because if you change the atom, you have to be sure that you are also including the proper index. Otherwise, you are computing the population or departure coefficients corresponding to a different transition. Okay?
Yeah. Also, if you don't put anything there, the code interpret read that as is an LT line. Okay, yes. These are LT since the Stokes inversion. If you put some values there, the code understand that this is an LT line.
Yes, that's true. Yeah, thank you. Okay, so then I repeat it again. This is very important. So be sure that you know the levels that correspond to this transition in your atom level. Okay, and I will go back to the atom later. Okay. Okay, one thing, I'm just warning you about a lot of things, but there are also nice things. So if you remember with RH, we had to have a Kurux file that we fit with lines, and then we needed to check that everything was okay. So now we are simplifying this. So you have one file containing the information of the lines, this one. And then internally, DeSIRe will pass this information to RH, so you don't need to create a Kurux file. This is a simplification that we made in the process. Okay, then the wavelet grid. So now you are telling the code, I want to produce a profile. You know which transition you want to compute. You have here the atomic information. And now you need to tell the code how you want to compute it in terms of how large or small should be the spectral range you want to compute and the sampling. So in this case, it's the same as SER. So you provide the index that is in the lines file, and then you provide the initial wavelength and the final wavelength. And as I said, this is respect to the core of the line that is included here. So then it's respect to this wavelength, for example, in index 4. And then you set the spectral sampling that is in milliamps. Okay. Remember that you can have several lines together. So then it means that for the same spectral range, you can have the same line. So you don't need to divide it. For each line, you don't need to have an entrance. So in this case, I'm saying that levels line 6 and 7, I want to compute them together. And if we go back, so you will see that 6 and 7 are the traditional 630 nanometer iron lines. So then it's better, they are just separated one Armstrong. So it's okay if you just compute them together. And also, it's important to remember that, again, this wavelength is referred to the line core of the first index. Okay, so then here we are starting at -700 milliangstrom respect to 6301. Okay, so maybe, and this is a bit special because now we are adding non-empty lines. In the past with photospheric lines was not so important, but now imagine that you want to have multiple lines, but we will have it in next tutorial in the wings of the calcium line. So then you will have, imagine that the core is like in the middle of my face. Then you have lines in the left side and lines in the right side. So you can start with the index of the line in the shortest wavelength and then define a spectrum from there. So it will be like, imagine -700, and then you have to cover all the line. So you have to go maybe like 10,000. Or you can say, well, I prefer to have the wavelength vector referred to the core of the calcium line. That is the biggest one and the one that I'm most interested on. And then the other lines, they will be there. So then for that, you can just set, imagine 4 is calcium, and then you have line 10, line 12, and line 13. And imagine that 10 has a shorter wavelength. It doesn't matter in this case. What you are saying is that the spectrum will be, the computed spectrum will be from -4,000 to 4,000 respect to the line core. And if line 10 is closer to that 4,000, then you will have it there, and you will have everything referred to the calcium line. We will practice this, but essentially it doesn't matter if you put index that are not that are in a different wavelength. The important thing is that the first one is the one that defines what is 0 for the range that you provide here. Okay, and usually you may want to have this for the chromospheric line that is much broader than the photospheric line. Okay, any question? No? Okay, thank you. So then abundance, it's a SER file. It's probably something that if you have worked with abundance files in the past, you will know these numbers. And again, the important thing is we have one file, and these values are the same we use when solving the non-empty problem with RH and also when working with DeSIRe. So we have everything as consistent as possible. Okay, solar coordinates. Okay, I think I don't have it here. Okay, let me open it. It will be input like here. Okay, so solar coordinates, very simple file for entrance. I think there are some combinations, but in general, this is the default one. The first and second is X and Y in arcseconds, where 0 means this center. And then if you move to this center, you can change this to different values like -400 plus 700. And then these latter two values, it will be the velocity, the Vx and Vy velocities at those points. So if you want to reproduce some specific scenario. But if you put 0, 0, 0, then it will be the ideal case. Okay. So then this covers the SER files, or almost identical SER files. So now we move to RH files. Okay, I hope you are following me. And then here, the good thing is that we try to simplify it a lot. And in fact, our recommendation is that you may not need to change this file. Basically, everything is default, and sometimes we overwrite it from DeSIRe. And the idea is that most of the things are commented. So you have the atoms and the molecules. This is a standard RH. Here you may want to play. This is something that you may want, but I think 200 iteration is usually okay for most of the atoms, but maybe you want to change it. And then you should not change this one unless you are not working with full Stokes vector. But I think, yeah. Well, you can experiment. Then this one, as I said, if you are using DeSIRe cubic from the instruction in the control file, then the best thing is also to have it here. It is the baseline. So even if you comment this line, RH will use this configuration, but we wanted to have it explicitly so you can really know which one you're using. And this is also again related with iteration. So if you know more or less how the code works with a given atom and you prefer to change this a bit, then that's okay. And this one is very important. If you remember, we are providing the atmosphere to DeSIRE in SER format, so no information of hydrogen population. And in general, we are doing inversions where sometimes we don't call RH. So in general, we don't have the non-LT population for the hydrogen atom. So then you should always, unless you tune the code, you should always have hydrogen in LTE because it's something that we compute every cycle and just pass it to the code. And then the code knows that you are working with hydrogen in LTE. Okay. So this one, try to keep it always on. And then you will see that the rest of the options, most of them are just commented. If you have experience with RH, maybe you want to try something different. But sometimes be careful because maybe we change a bit the meaning of the sentence, or maybe it's not used. So just if you want to have something a bit more in detail, maybe you should contact us just to check that that function is still working in this side. Okay, so very simple. My advice, don't touch it, and maybe iterations, but in general, at least for the first and simple test, don't modify this file. Okay, so then we are calling atoms to provide information of which atoms we are going to solve actively. So it means that we are going to compute the populations in non-LT. And then which atoms we are calling in passive mode. That it means that we are just using them for getting our accurate or a more accurate background opacities. So then in this case, there's only one active atom, that is calcium 2, and the rest are passive. If you remember from RH tutorials, you can have any number of atoms as active. It doesn't matter how many you have, and you can solve. Imagine that you have an observation with, I don't know, hydrogen, magnesium 1, and calcium 2. You can solve them all together. It's fine. And one thing that is important is if you see passive, I have all the passive atoms in this bar atoms folder. Remember that it was a default folder in the DeSIRE distribution. But then the active one, that is the one that I modified, I put it in this folder. You can put it in another folder, but in my case, I prefer to have a local copy every time that I'm doing something different. So if I'm doing inversion of something, I just want to have the atom that is active there. Because if you change something, it could improve the results or it could make them a bit worse. And then in any of the cases, you are just producing an effect on that local run. But if you change the atoms in bar, then every time that you run DeSIRE for anything, it will have an impact. And if the change is for the worse, then you will have an impact on all the computations, and it will be difficult to trace that error for us. So my advice is everything that you actively change, try to have it somewhere else. So then you can always go back to the default version that in principle, they work okay. Okay, so then molecules is the same as atoms at input. You have a list of molecules. They are in the default folder. They are all as passive to have a better estimation of the background opacities. And as we said in the RH tutorials, we don't usually solve them as an active. And it's possible, but if you want to do that, you probably need to contact Han or someone else that have already done this with RH. But in DeSIRE, I think it's not going to be common to have solving molecules in active mode because it requires some fine tuning that Han needs to probably help you with. Yes, thanks, Han. Okay, so Han sent a comment and it says because it will not be recorded, Han. So, so do you want?
Yeah,
you
sorry.
can say it. You can say it. Yes. Yeah.
No, I didn't want to interrupt you.
Yeah. No, it's fine.
No, if you are ever in doubt what flags you've set, and which I've set by default, you can run with the -s flag, and it will give you a printout of which ones you've set explicitly and which are set by the code by default.
Yes, yes. Okay, thank you. Okay, so then, but it's good that you interrupt me because I can breathe, because these days my throat is still not so good. Okay,
Okay.
thank you. Okay, so then we are getting close to the end of this long list of files. So then we have the atomic model. Again, we covered this in a lot of detail in our age class, so I will just quickly go through it. Important thing is that it's exactly the same format that we use in RH. So if you have been working, preparing an atom for your studies with RH, then you can just copy this file in the DeSIRe distribution and it will work. Okay, I will not cover it. The important thing is that, again, you always have the information about the levels that are involved in the transition, and this should be provided to DeSIRe because we want to know the levels involved in the departure coefficients that we want to compute. Okay, this one is the one that we prepared in the RH class. So it's we are using a lot of points in the spectral range. Remember that we are solving both sides of the line. And then if you remember those points, these 150, they were divided in half. And then half of them in the Q core, they were linearly spaced. So then we are covering the core with a linear sampling that is a very fine and dense grid. And then in the case of QWin, we are telling the code that the points can be separated. Half of those points will be separated in a nonlinear scale. And the values of 10 and 200, if you remember, they were in Doppler units. So then if you still don't know, if you forgot about that, just check the class. I think I put it the reference somewhere, but I think it was class 2. Yes, here, class 2. And then you can revise that again. But essentially it's the same one that we had for RH. Okay, what I have here. What is that? This is okay. And yes, and just one thing, and this is the important one. So you configure the atom model in the same way for RH. So RH is receiving it in the same way, but the final product that you will get from DeSIRe is a bit different. It's first, as I said before, the spectral range will be uniformly sampled. So then you don't need to interpolate or to think too much about that. So the grid that you are providing to DeSIRe is the one that you will get at the end. And then, as I said, if you are using the standard dot pair profile extension, then you will get it also normalized to the local intent and to the continuum. Okay, so then this is a bit different. And then, yes, and I think that's all. Okay, so then we are going to just run a very, very simple case just to start things and then allow you to check in at home before the next class if you want to try things and check that you follow the class. So, but before that, is there any question about all those files or something that you didn't understand because it's new? Maybe that or
Carlos, yes.
Yes.
Can you repeat, please, why we need to set that hydrogenate true? Because I checked all my RH runs and I've never had set it this as true in my runs.
Yes. So because you are providing an atmosphere that already contains hydrogen in non-LTE, right?
Yes.
Yes. So the idea is that the atmosphere that we are providing this side is this one. So there's no information about hydrogen in the atmosphere. So it's just the thermal part, the magnetic part, and there's no information about hydrogen. So in general, you are not solving also the hydrogen atom. So then the code doesn't have any way of computing that population in non-LTE. So then we assume that the best thing was to just compute internally every time LT populations. That is very simple because we are solving the Saha-Boltzmann equation. And then inform RH that the atmosphere that we are providing, it contains hydrogen populations, but they are computed in LT. Okay.
Yeah, I see now. I see.
Yeah.
Because yes, in RH models we have that extra part in them.
Yes.
Yeah, all the vol models have, and so the reason why this is different is some of the background opacities you need the hydrogen opacities. For instance, for the hydrogen bound 3 background opacities, you need the populations of the different hydrogen levels. So what the code does, if you don't provide them, it will assume LTE populations for those values, and you get slightly different background opacities.
Yeah, I see.
Yeah.
I also have one more general question.
Yes.
So I guess DeSIRe is working for Balmer lines in the inversion mode, right?
Mm-hmm.
Because I know that many inversion codes are struggling to invert the hydrogen lines, Balmer lines in general, but I guess RH does not have any problem to synthesize the hydrogen lines, so it will be same for inversion, right?
Well, yes, I mean, it will work as good as RH, but I'm not sure RH is working so well with hydrogen, I mean, with H-alpha, because they are complex lines. So maybe Han, you want to add something?
No, yeah, I think the problem does not lie in the inversion codes, but in the physics of the problem. The Balmer lines are very much scattering lines, so they don't carry much local information into their line profiles. So the inversion of a Balmer line is just a fairly ill-posed problem because the epsilon, if you will, is very small.
Yes.
Yeah, even if you don't include the polarization, right?
Yeah, the polarization in these lines is very small because they are hydrogen is a light element, so the Doppler broadening is much larger than the Zeeman splitting typically, and especially linear polarization Q and U depends on goes with the square of the ratio of the Zeeman splitting over the Doppler width. So Q and U are typically very small in the Balmer lines.
Yes. So what I would like to say is that, in fact, our impression, and we haven't really tested, our impression is that maybe if you have, I don't know, H-alpha data from SSD and you want to embed it, the code will work, but maybe as Hans said, it's not going to be a very good solution. But our impression is that it probably will work if you add something else. So if you have calcium 2 infrared and Balmer lines like H-alpha, H-beta, and you embed all of them together, we believe this will improve the results of embedding only calcium. But this is something that we want to test even with you. So people that have data of, I imagine, H-alpha and calcium, I think embedding them together will improve the results. And DeSIRe can do it. But only H-alpha, we are not so sure about that.
I see.
Yes. So in other words,
some extra constraints, right?
Yes.
Can come from other lines.
Yes. And at the same time, you can have information from different ledgers that the calcium cannot see, for example, or are not so sensitive to that. So in other words, if you have observations where you had H-alpha and calcium, our recommendation will be embed them both.
Okay.
So it will be a new approach, I think, with respect to previous case.
So to give you an example, it's simple to do a calculation with the H-alpha line. And for instance, you take a Val-C model, you calculate the line profile, and then you take a Caruso model, which has no chromosphere at all. And the line profiles are almost identical. And so you're providing not very useful information by providing the line profile to an inversion code. in H alpha because it cannot decide whether there should be a chromosphere or not.
Yes.
Mm.
Yes. Yes. But if you have the constraints from the calcium line, then we believe it will help. So I would definitely try only calcium line and then calcium plus H alpha, for example. And we hope this will give some constraint and additional information.
Yes. Okay.
Okay.
Thank
Okay.
you.
Yeah, thank you. So any additional questions?
Yes, Carlos, I have, I couldn't understand this use of this coordinate file, POS dot.
Yes.
Or,
This one. Yes.
yes.
Yes. So this file is for essentially telling the code where your observation was. So imagine that your observation is a heliocentric angle 0.7, but you know that this is, I don't know, imagine x minus 400 and y 550. So then you provide here this 400 and then 550. And then if you have the local velocities and the rotation, the velocity rotation at those coordinates, then you can also provide it here. And then the code will run, and then it will try to include those those effects on the final profile. So when comparing with your observation, the code will add an extra correction that is related to the heliocentric angle where your observation was at.
Yeah, if you keep these values in 0, even if you are running the code in a different position in the sun, if you put 0 there, the code interprets that you are in the line of sight. It doesn't matter. You can run in this case, but the output is the line of sight atmosphere. It's not. It knows the local reference frame. I mean the y exit, the height exit is not perpendicular to the surface. In this case, if you put 0, the code interprets that you are running in the
center.
In the center, and then in fact you are running the line of sight. Then all the result is along the line of sight. It's not okay.
And the last two ones are
is for velocity. The both components of velocity.
Yeah, for rotation of the sun to compensate.
Exactly. Exactly. For instance, you have the information of the rotation of the sun. You can, because Vx normally is the rotation,
yes.
And then depends on the latitude. Okay, and it has a big value there.
Okay.
Yeah, okay. Yeah.
Okay.
Thanks.
Yeah. Thank you. Okay. Any?
Yes, Carlos.
Hi, Alberto. Hi.
Hi. So I have a question. You have mentioned that the observed dot pair is normalized to the near local continuum to the line. This is, I guess, independent to the spectral range that you are using in your synthesis or your inversion defining dot grid. Or in another way, imagine that you are synthesizing or inverting just the core of a line, and for any reason you are not going very far. Does DeSIRe found the local continuum?
So the idea, and Basilio can correct me if I'm wrong. So the idea is that we have all the continuum. So we computed the continuum of the full spectrum without adding lines. Okay, so we have all the continuum with a nice spectral sample.
Okay.
So then if you said that your line is in 634, we will have a continuum close to that position.
You have a database with all the continuum.
Yes.
Okay.
But that, and I think I said, but if not, I would repeat it. And this was created from the HSRA model. Okay, so it means that the one value is the one that you get with the HSRA model. So then if your model is hotter or cooler, then your continuum will not be exactly one. But the idea is that you can always refer to the HSRA.
Yeah, you have a reference. Okay, thank you very much.
Okay,
thank you.
Okay, Basilio, was correct what I said?
Yes.
Okay, thank you. Okay, so then any additional question? No? Okay, so then something very simple, an example. We want to compute the calcium line plus the two iron lines And then we want to have something very simple. It will be the DeSIRe model with 1000 Gauss of magnetic field, 45 degrees of inclination, and then 70 degrees of azimuth. And then we add a velocity just to check that we understand the signs of the velocity and to check how the lines behave. But everything is constant with height. So, sorry. So it will be a symmetric profile. So it will be something simple, but we will improve this in the next tutorial. So we read the atmosphere. We just change some of the values: magnetic field, velocity, inclination, and azimuth. We write the atmosphere in this value input.mod. So then if you go to synthesis, you will see that this is the atmosphere that we are providing. And then we just run DeSIRe here. So running DeSIRe, it will mean that it will read the wave grid file. So then if we go to the wave grid file, we are saying that we are synthesizing line 4 and line 6 and 7 together. If you go back to the lines, I'm going to do it slowly. If you go to the lines file, 4 is the calcium line, and 6 and 7, they are the iron 630 lines. And in the case of 4, we want to have Nonempty. So then we have to provide these 2 columns with index, and then 2 and 4 should match with the atom file that you are providing RH through the atoms.input. And in atoms.input, you are saying that the active atom is this file that is in this folder that I opened here. So then the transition that goes from the lower level 2 to the upper level 4 is exactly the 8542 transition that you are going to compute. Okay, we will repeat this process next week, next class. Okay, so we just run the code, we read the profiles. Let me see if this works. So now you saw that it was saying I was calling RH, and this is what you get. If you remember, I just said 4, 6, and 7. 4 is 850 and 6 is 630. So they are in fact shift. So this wavelength is different than this one. And now this is just a profile you get from RH. Okay, this is the intensity one. So we can tune this a bit. And what I'm going to do is I will read all the entrance that you have in the profile file with index 6. Okay, and this will be our iron blend wavelength, that it will be this one. And you remember that it was in milliangstrom, so I'm going to transform it to nanometers, dividing by 10 to the 4. And then this value here is the same that you have in the lines file in entrance 6. Okay, so with this, I will have the wavelength in the absolute wavelength units, and so you will have everything in nanometers. And then the profiles will be those that will have the same index, 6. Okay, we can do the same for the calcium line, and in this case, index 4. We again compare that this one should be the value that you have in your lines file. And then you just picked the profiles that belong to the index 4. And this is the plot that I'm going to do here. You can check it later at home, but basically this is calcium profiles and these are iron profiles. Okay, and then if we go to the class, I put it here already. So this is the results from our first synthesis, and you can see that these are the 2 iron lines. I put it a vertical line just to show you that we said that we wanted to have a redshift of 3 kilometers, and you see that the lines are to a longer wavelength, so it's a redshift. And then you have signals in Q, U, and V because the magnetic field is strong and the inclination is 45 degrees. So and the azimuth is 70. So none of the Stokes parameters are 0. So you always have signals. And then the same for the calcium line. Okay, here the spectral range is a bit larger, so then it seems that it's very, very long, and then you have something in the middle. But this is what atmospheric lines look like. And again, I forgot to put the line here, but it's also shifted to the red because the velocity was constant with height. And then you have that Q and US signals are reasonable for a chromospheric line, around 1–2%. And then Stokes V signals are also strong because we have 1000 Gauss and they are close to 10%. Okay, so with that, you can try at home to run your first non-LT computation with DeSIRe and try to read the files and to understand what I did here. But basically, this is all I wanted to show you today. It was, I think, a long class because we cover all the files. But then slowly, when we tune things in the next tutorials, I will always emphasize we are changing this and this means that, and then it's affecting this file or the other file. Okay, but I hope this, if you read it or if you watch it several times, and also if you read this very carefully, I think it's like a manual. So then you will always have something that you can double check to be sure that you are changing what you want to change and understanding the amplitude of the change that you are introducing. Okay, so then I will go back to the presentation, and then unless is there some question, I think no. So homework, just try to understand what we covered today. There were a lot of files, and some of them we already checked them in the SER and RH tutorials, but I think it's still a lot when you see it for everything together. But try to check if you follow everything, and if not, just write down the questions, and in the next class we will start just with questions and doubts that you have when you were watching this video. And then next class it will be doing synthesis. I will try to run several examples. I don't know if I may think that is not long enough, and maybe we will try to compute response functions with those samples. If not, we will just focus on synthesis, because I think it's very important that you understand all the files that you need to configure and what things you can change before just starting with inversion. Okay, and then yes, and the idea is that we will start with something simple, and then we will try to get to something close to the first observations that we will have this year from VISP on the KISS. That will be calcium with some satellite lines and two calcium lines together, and also the iron lines. So we will try to get close to that. Okay, so next class on 2 weeks, on Friday. And before letting you to go away and relax and forget about all the things that I said today, is there any last question? No? Okay, so then enjoy the weekend. And I'm sorry, I know today was a very long class and very complicated, but we will get used to it, and it will be much easier. And I hope also my voice will be a bit better. So then see you in 2 weeks, and thanks a lot for joining us today, and take care and have a nice weekend.
Thank you, Carlos.
Thank you,
Thank you
Carlos.
so much.
Bye.
Bye, everyone.
Bye.
Bye.
Bye. See you. Bye. Okay. So then I will stop sharing.